This is part 2 of section 3.4. We want to use the rational zero theorem to find the zeros of this given polynomial. Okay, so I notice that I have integer coefficients. So the first thing I want to do is I want to list all of my possibilities. Well, 2 is my a0, so the p comes from everything that divides evenly into 2. And that would be plus and minus 1 and plus and minus 2. My a sub n, or my leading coefficient, is a 2 as well. So my q possibilities are also plus and minus 1 and plus and minus 2. So my list of potential zeros, I create every p over q combination I can. And I get 1 over 1. And then I get 1 over 2. And then I have 2 over 1, which is 2. And then I have 2 over 2, which is also 1. So I've gone from a potential infinite number of solutions down to just 6. Now on this one, we're actually asked to find all of the zeros. So what I need to do is I'm going to use synthetic division to check each of these possible answers. And what we want to find is we want our remainder to equal 0. And if our remainder is 0, that means that the number we tested was a 0 of the original polynomial. There is no surefire way to find the correct answer immediately. There are ways to make better guesses and to guide what numbers you choose to test first, but there's no hard and fast rule, and a lot of it comes down to luck. So let's just test, I don't know, positive 1. Let's go with 1. If I'm testing 1, I put the 1 in a half box here, and then I'm going to put my coefficients right here. I need to make sure that everything is there. I have a third, a second, a first, and a constant. So everything is there. So I have 2, -5, 1, and 2. Bring down your first. I get a 2. 2 times 1 is 2. -5 plus 2 is -3. -3 times 1 is -3. 1 plus -3 is -2. -2 times 1 is -2, and then when I add those, I get a 0. That tells me that 1 is at least one of my solutions. Okay, so basically, another way of thinking about this, and we're going to get more into detail this in a minute, is that if I took 2x cubed minus 5x squared plus x plus 2. This factors as x minus 1, because if I set this equal to 0, I'm going to get 1 as an answer. X minus 1 times this, whatever this is. And remember, we always start with 1 degree less. So this is a 3, so I put an x squared here and an x here. Now, it might be that I need to keep checking more numbers, okay? And when I go to check more numbers, I would use this and not this. You'll see a lot more of that in a minute. But what you want to do is eventually, you're going to be able to get it down to where you have just a quadratic, okay? And then once you have it down to a quadratic, we know how to solve this just by using the quadratic formula, or you can try to factor it if you want to. If I use the quadratic formula on this, I have x is equal to -b, so positive 3, either plus or minus the square root of b squared, -3 squared, minus 4 times a, which is 2, times c, which is -2. And this is all over 2 times a, which is 2. So if I do the calculations inside of the square root, I have 9 minus 4 times 2 times -2, and that is 25. So I have 3 plus or minus the square root of 25 over 4. Now, since this is a perfect square, then that tells me that I'm going to get 2 rational solutions from this. And I need to calculate both the plus version and the minus version. So if I have 3 plus 5 over 4, that is 8 over 4, which is 2. And then if I do 3 minus 5 over 4, I get -2 over 4, which is -1/2. So I have my 3 solutions here. My first answer was 1. My second answer is 2, and notice that 2 was on our list of possibilities. And then our third solution is -1/2. And -1/2 was also one of our 6 possibilities. Okay? So this is kind of what we're going to be doing. If we had guessed something here that did not work, then we would have gotten something other than a 0 here, and we would have just scrapped this one, tried the next number, and gone on. Basically, it's a process of elimination until you find your first solution. All right, so let's look at a couple of properties. If a polynomial function has degree n, then counting multiple roots separately, the equation will have n roots. Roots, same thing as zeros. For this problem, our degree was 3. We expected 3 answers. We got 3 answers. Now remember, if we count multiple roots separately, so imagine that I didn't get 1 and 2 and -1/2. I got 1 and then 1 again and -1/2. We would count that separately when we're checking to whether or not it has the degree, but you would only really need to list the answer once. Okay. So whatever the degree is, that's how many answers I expect to get. Not how many rational answers I expect to get, just the number of answers, period. Okay. Now, part 2 of this is if a plus bi is a root of the polynomial equation. So if we have one complex answer, then it's conjugate pair, which is the same thing, but if this is a plus, this is a minus. The middle sign changes. If this is a root, this is also a root. Complex roots always occur in pairs. And the reason for that is if you think about the quadratic formula and you have plus and minus that square root, the reason we get a complex answer is when we have a negative number inside here. So if you have a negative number inside here, you're going to get an I, and then you're going to get a plus version of it, and you're going to get a minus version of it. That's why these come in pairs. Okay. Now let's talk about Descartes' rule of signs. This is pronounced Descartes. He's a French philosopher / mathematician. He is the one responsible for coming up with our graphing system. The rectangular coordinate system is also called the Cartesian coordinate system, coming from René Descartes, Cartesian. He's also the philosopher who said, "I think, therefore I am." A lot of us have heard of that, even if we don't necessarily know what he was talking about. Okay. So what this is going to do is it's going to give us a little bit of guidance about what kind of answers we get so that we can make better choices as to the first numbers we check. All right, so if we have a polynomial function, and this time it has just real coefficients. So this one isn't as restrictive as the rational zero theorem was. This one required that we had integer coefficients, no fractions, no square roots, just integers. This one, as long as they are real numbers, meaning no i's involved anywhere, this will work. And what this does is it will allow us to determine the number of positive real zeros, and this will include any square roots we may have. It will include any imaginary numbers we have. But the number, well, not imaginary, sorry, real numbers, that would be complex. The number of positive real zeros is either equal to the number of sign changes or is less than that number by an even integer. Okay, now what do we mean by this? By sign changes. I'm going to come back up. I'm going to rewrite the problem we did at the top of this page. We had f of x equal to 2x cubed minus 5x squared plus x plus 2. To find the number of positive real zeros, we look at just plain f of x, which is what we have right here, and we want to make sure that our powers go down, and then we're going to count the number of times that our sign changes. So we go from a positive to a negative, that's one sign change. From a negative to a positive, that's a second sign change. And then positive to positive, that's not another one. Okay? So from f of x, I had 2 sign changes. Okay? So this says that I will either have, it will be either equal to the number of sign changes. So this says I will either have 2 positive real zeros, or it will be less than that by an even integer. So basically what you want to do is you want to keep subtracting 2 until you get any, you can't go anymore. So I either have 2 or 0 positive real answers. Okay? If I had 4 sign changes, it would be 4 or 2 or 0. Basically, what we're doing is we are subtracting off the possibility that we have a pair of complex answers. That's why we're reducing it by 2 every time. Okay, so from this, the problem we worked, we either have 2 or 0 positive answers. And if you look at our answers here, we had 2 positive answers. Okay? Now, how do we find the number of negative real zeros? Well, that's either equal to the number of sign changes of f of negative x, or is less than that by an even integer. Now, we've done this f of negative x business before when we were talking about odd functions or even functions. If again, I'm going to use this one that we used before. If I find f of negative x, that is 2 times negative x cubed minus 5 times negative x squared plus negative x plus 2. When you cube a negative number, your answer is negative. So this is the same as negative 2x cubed. When you square a negative number, it's positive. So this is negative 5 times x squared, so minus 5x squared. This is minus x plus 2. Now let's count the number of sign changes in this once we've plugged in a negative x. It's negative, and then negative, and then negative, and then finally it changes to a plus. So that's just one sign change. So the number of negative answers is either 1 or 1, because if I subtract 2, then I'm in the negative, and so I can't have a negative number of answers. So I have 1 negative real 0, and up here I did have 1 negative real 0.